You now know why you need control and how a control loop works in general. In this video, I will focus on a PID controller specifically. I will be telling you what a PID controller is and how it works in our exoskeleton. PID control works on the basis of a feedback loop on the bottom of the diagram and an error signal. In our case, we compare the gait path, as you can see at the start of the diagram, with the actual gait performed at the end. The error between these two is the input of the PID controller. Using P, I, and D action, the controller aims to decrease the error. Feel free to pause the video and take a moment to look at the diagram on the screen. See if you can understand the basic loop before we get into the specific PID action. The P stands for proportion. If the system is controlled with a P controller only, the error is simply multiplied with the proportional gain, so the P value you add to the system, usually written as Kp. In this equation, the error is written as E. The larger the error, so the further away the actual path is from the reference path, the more P value will react. And also, the larger the P, the more aggressive the exoskeleton reacts and faster you reach the desired path. Look at the graphs on the screen here. When we increase the P value, the actual path nears the desired value faster. But you can also see the drawback of using a P controller only. Overshoot is a common issue, meaning that the error is further increased. This can lead to unstable behavior. To prevent this, you can add I action, which is short for integral. Then you have a PI controller. But how I action actually works, you will find out yourself later this week. Lastly, you can say the D gain, short for derivative, looks into the future. If you get close to your reference path too fast, the D gain will hit the brakes to slow the motor down. Or the other way around, increase the action. It will therefore attempt to minimize overshoot. These three gains must be tuned, and that is also what we do with our exoskeleton. If your P gain is high, you will have large overshoot, because the system acts aggressively to the error, and this will result in a lot of oscillation. But if your P gain is too low, you will reach the reference path very slowly and not at all. If you have tuned the D gain well, you can prevent overshoot and slow down at the right moment. But you do not want the system to slow down too much. Essentially, for a large part, it comes down to trial and error and creating a feeling for it. For example, if there is a lot of overshoot when performing a gait, our control engineers might want to decrease the P gain or increase the D gain. But you do not want to add too much D gain, because you do not want to slow things down. So you need to take that all into consideration when finding the right tuning for all joints of the exoskeleton. I hope you now understand how the PID controller works. Thank you for listening and see you in the next video.